Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is The Fundamental Theorem of Calculus. Remember, you want to be an active learner while watching this video. The area under the graph of a non-negative continuous function f over an interval ab is determined by an area function a. And here's a picture of that, what they're talking about, which we found in the last section is an antiderivative of f. That is, the derivative with respect to x of a of x is equal to f of x. Now we have established this fact for cases where f was a constant in the last section and f was a linear function using formulas for area. Now when the graph is a curve, we saw we could approximate the area under the graph using a Riemann sum, and that suggested that a general method for calculating the area was to take the Riemann sum and take a limit. So what we're going to do now is we're going to talk through and we're going to see that the derivative, we're going to calculate the derivative of this area function. Now to take the derivative, where you're going to start is you're going to look at the difference quotient. So you'll look at a of x plus h, which is this, minus a of x, which is this. And so the difference between the two is a of x plus h minus a of x is this little bit here. And notice that now we have just a tiny interval x to x plus h, and we have that. And you see that since this is a continuous function, it really doesn't change much. It's pretty much, it's just f of x kind of in the middle of there. It doesn't change much from that. Okay, so that means that the area of this rectangle then is going to be, this side is going to be h, and that's pretty much f of x. So a of x plus h minus a of x is approximately equal to h times f of x. So if I divide both sides by h, I have that this is approximately f. So if we let h go to 0 on both sides, on this side we're going to get a prime of x, and on this side we're going to get the limit as h goes to 0 of f of x. Now this doesn't depend on h, so that means that this side is a prime and this side is just f of x. So we proved the following theorem. If f is a non-negative continuous function on 0 to b, and by the way, this is important in this theorem that it's non-negative, and let a of x be the area between the graph of f and the x-axis over 0 to x, where x is between 0 and b, then a of x is a differentiable function and the derivative of a of x is equal to f of x. So Theorem 4 answers the question posed earlier. The derivative of the area function is always the function under which the area is being calculated. We now adapt Theorem 4 for the case where f is defined over any interval ab. So here's our picture over here. Referring to the graph, we can see that the area over AB is the same as the area over 0 to B minus the area over 0 to A, or A of B minus A of A. That's capital A of B minus capital A of A. Now in the first section in this chapter, we found that a function's antiderivative can differ only by a constant. Thus, if f is another antiderivative of f, then a of x is equal to f of x plus c for some constant c, and so the area is capital A of b minus capital A of a is equal to f of b plus c minus the whole of capital F of a plus c, and that is capital F of b minus capital F of a. So this result tells us that as long as an area is computed by substituting an interval's endpoints into an antiderivative and then subtracting any antiderivative, and any choice of c can be used. But it's the same c here as it is over here. And so you might as well simplify your computations to choose 0 as the value of c. Let's do an example. We want to find the area under the graph of f of x is equal to 1 over 5 x squared plus 3 over the interval 2 to 5. That means that this is what we're doing. This is the graph of 1 over 5 x squared plus 3, and we're finding the area under that curve and the x-axis going from 2 to 5. So this yellow area is what we're finding. Well, the antiderivative of this is going to be the 1/5 just sits there. This is x squared, so you add 1 to the exponent, divide by the new exponent, we get 1 over 15 x cubed plus 3. And when we go to 3, that is 3x to the 0. The 3 just sits there. We add 1 to the exponent, getting x to the 1 over 1. We get 3x plus c. But then what we're going to do is we're going to be evaluating that by putting 5 into this function and subtracting that function with 2 substituted in. So here's what happens when you put 5 in, and here's what happens when you subtract the whole of f of 2. And realize you're subtracting the whole of capital F of 2. Now you might say, well, Jim, you're not going to make us do calculations like this. Yes, I will. So make sure that you can do this and follow this. Then we do the calculations. You should verify these calculations. It's good practice for you. We find out that this area is exactly 16n 4 over 5. 16n 4/5. Kind of amazing to me that you can actually calculate that. Let's look at another example. Example 2. Find the area under the graph of y equal x squared plus 1 over the interval from minus 1 to 2. Here's the picture. Again, it's a positive function, and we're finding this area here that's shaded gold. Okay, in this case then, this is lowercase f of x is x squared plus 1. So if we integrate this, we're going to add 1 to the exponent, getting x cubed, and divide by the new exponent, which is 3. So that gives us, for capital F of x, x cubed over 3. And here it is 1, and 1 is x to the 0, so that is add 1 to the exponent, divide by the new exponent, and we get x. And we're taking c to be 0 because that's much simpler. So now what we're going to do is we're going to substitute 2 and minus 1 in the endpoints, and we're going to find out the difference between capital F of 2 minus, this is capital F of minus 1. So this is, here's what we get when we put 2 into this capital F of x minus. And this is what happens when we put minus 1 in here. Now there's a lot of calculation here. Make sure you can follow this and do that. But when we simplify this, we get this number minus. When we simplify this, we get this number. We distribute that minus sign, combine terms, and we get 6. That's this area. Let's do another example. Let's look at y equals x cubed. Here's a graph of y equals x cubed. And we're actually making this into a word problem. So this represents the number of kilowatts generated by a new solar array each day, X days after it's going operational. So you see it starts doing more and more and more because it's collecting more and more solar energy, I guess. Find the area under the graph from 0 to 5 and explain what this area represents. Okay, well, this is the function, and we want to find the area between 0 and 5. So we find the antiderivative of this, add 1 to the exponent, 3 plus 1 is 4, divide by the new exponent, and so that's x to the 4th over 4. Then we're going to calculate the difference f of 5 minus f of 0. So we take 5 and put it into there. We get this. We're subtracting. That's the minus sign. And we're putting 0 into this function, and we get that. And so the answer is 625 over 4, which is a fine number. But also that's 156 1/4. The area that we're talking about here represents the total number of kilowatts generated during the first 5 days. And the units on this are going to be kilowatts per hour per day times days are going to be kilowatts, because it's the product, because an area is the product of the two. This was kilowatts generated per day, and this was number of days. Now, so how do we calculate then this? And this is the same thing as talking about the definite integral from a to b of lowercase f of x dx is going to be capital F of b minus capital F of a, where this capital F is any antiderivative of lowercase f. Capital F is any antiderivative of lowercase f. You see how the antiderivative studies we did back in chapter 4.1 are coming into play here. Okay, so this is called evaluating definite integrals, and it's called integration. I think you want to know, and you've seen in the examples, that this is a number, not a family of functions. So when we were talking about indefinite integrals, you got a family of functions with a plus c. Now you're getting a number. It's called integration. The numbers a and b, the limits, are the limits of integration. And it's often convenient to use some intermediate notation. So this is the integral from a to b of f of x dx is equal to capital F of x evaluated, and a lot of times we do b as the upper limit and a as the lower limit. This is an intermediate thing, but then we substitute that in and we subtract the result. Again, taking c to be 0 is convenient. Okay, so let's practice some of this, and we're going to use some of our properties and some of the identities that we know. And again, you do want to commit these to memory. These are not going to be in grace notes. So here we have the integral, the definite integral from -1 to 4 of x squared minus x dx. Now, what we can do here is we can do this term by term, or we could do it all together. And it looks like what we do down here is we do it all together, but we're really doing it term by term. So we're saying this is going to be add 1 to the exponent divided by the new exponent, that is x cubed over 3, minus this one, I add 1 to the exponent divided by the new exponent, that is x squared over 2. I evaluated at 4n minus 1. So first we put the 4 into this expression, getting this, minus this minus sign is the minus sign from the fundamental theorem of calculus. Well, I guess we really haven't called it that yet, but we will. But this minus sign is what happens when we're taking this one minus this. Remember, it is minus the whole of this. We do a lot of computations. You should check these computations. That's great practice. And at the end of the problem, we say that this is 14n 1/6. Let's look at this one, problem B. Now here we're finding the definite integral from 0 to 2 of e to the x dx. Now the antiderivative of e to the x is just e to the x. So this is equal to e to the x 2 minus e to the 0, e squared minus e to the 0. And that is exactly e squared minus 1. This is the exact answer. If you left the answer this way, I would count it right. But if you plug it into a calculator, you would get approximately this number. Let's look at problem C. This is the definite integral from 2 to 5 of 1 over x dx. Now, you have memorized that the antiderivative of 1 over x is the natural logarithm of x, and I'm evaluating that at 5 and then at 2. So I put in the 5, I get ln of 5 minus, and this is ln of 2. Now this is the exact answer. If you plug that into a calculator, you find out this is approximately what it is. But this, again, is exact. On problem D, what we're doing is we're going from -4 to 1, the integral, the definite integral, from -4 to -1 of 1 over x dx. Now here, in the previous problem, we're going from 2 to 5, so it's always positive. But remember that our equation really said that it was the natural logarithm of the absolute value. So this is now the ln of the absolute value of x. We put in 1 minus, this is the ln of -4. Now the natural logarithm of 1 is 0, and so here we get the minus the natural logarithm of 4. That is a negative number when you put it in. Here's a statement of the fundamental theorem of calculus, and you have to go back a long way, but you see this limit here of the Riemann sums is the same thing we talked about as being the definite integral, and we know that the definite integral is found by capital F of b minus capital F of a, where capital F is any antiderivative of lowercase f of x, and you might as well take c to be 0. Now later on we'll see that more than one variable can be used, and when we are doing that, we might be doing integration by substitution. That's a preview of some coming attractions. Here we're just saying that dx indicates that the integration is being carried out with respect to x. Let's do some more problems. Find the area under the graph of y equal 1 over x squared from 1 to 10. Here's a picture of 1 over x squared, 1 to 10, and it's positive there. So our theorems certainly apply, and what we have here is this area. Now this area is going to be the definite integral from 1 to 10 of 1 over x squared dx, or it makes sense to write this when you're doing calculus, x to the -2 dx. So we add 1 to the exponent and divide by the new exponent, and we are evaluating that at 10 and subtracting that evaluated at 1. When we simplify this, doing the calculations, we get x to the -1 over -1, and that's the same thing as -1 over x, and we're putting 10 and 1 in. So when we put 10 in, we get -1 over 10. This minus sign is from the fundamental theorem of calculus. When I put 1 in, it's -1, so this is 9 over 10, or 0.9. You've really got to be careful with your signs when you're doing this, and arithmetic does matter. Suppose that y is profit in dollars per mile traveled, and x is the number of miles traveled in 1,000, and the function is y equal 1 over x. Find the area under y equal 1 over x from 1 to 4, and explain what it represents. Well, okay, so what we're going to do is, this is the picture. There is y equal 1 over x, and we're finding the yellow or gold area. So that area is going to be the definite integral from 1 to 4 of, this is going to be 1 over x dx, or dx over x. That's going to be the natural logarithm of x, evaluated at 4 and 1. Both those numbers are positive, and that is the natural logarithm of 4 minus the natural logarithm of 1. This is the ln of 4 minus the ln of 1 is 0. And so this is the exact answer, the natural logarithm of 4, but this is what it approximately is. And so considering the units, you got dollars per mile times thousands of miles, this thousands of dollars. And so this says that when you multiply that by 1,000, it's 1,386.30 approximately. That's rounded probably to the nearest cent. Now what we're going to do is we're going to talk about two integrals. Let's look at this integral. So this is the definite integral from 0 to 2 of x squared. You add 1 to the exponent, divide by the new exponent. You're going to put 2 in, and you're going to subtract when you put 0 in. So we put 2 in here, subtract 0, and we get 8 over 3. Now we're going to compare that to this one, but if you think about this, this one we can pull the minus sign through the integral, and or otherwise it's going to be minus x cubed over 3. We substitute numbers in, we get minus 8 over 3. So you see, if we have negative function values like we're going to have here, this area ends up being negative. If we have positive values, it ends up being positive. And you might be thinking, what happens if we have both? Let's look at that with this function here. This is y equals f of x equal x squared minus 1 over the interval from 0 to 2. Now it is negative here, and then it is positive here. And just looking at that, it looks like the gray area is going to be bigger, but you see this is going to end up being a negative number, this is going to be a positive number. And in fact, we calculate it that way. So here's what we do. The integral from 0 to 2 of x squared minus 1 dx, we integrate from 0 to 1 plus from 1 to 2. Now, this ends up being a negative number. This ends up being a positive number. So the net of the two is 2/3. And that's why I was talking about this being the net area. And again, we don't have to break it up this way. We can actually just do it straight up, as done here, and we see, oh, it's still 2/3. So the definite integral of a continuous function over an interval is the area above the x-axis minus the area below the x-axis. It is the net of the two. Here's another example. So consider this function, and this is the definite integral from minus 1 to 2. This is negative x cubed plus 3x minus 1 dx with respect to x. Now it looks like this, and again I'm just eyeballing this. This is the function, and we're going from minus 1 starting here to 2 over here. So you see it's negative here, it's positive here. But you see we don't have to break it up that way because we learned that the integral takes care of that. So the definite integral from minus 1 to 2 of the function with respect to x, we're taking the antiderivative now. So here the minus sign just sits there. We add 1 to the exponent, divide by the new exponent, plus the 3 just sits there, and we add 1 to the exponent, getting 2 divided by 2, so that it's 3 over 2x squared, minus, this is x to the 0, add 1 to the exponent, divide by the new exponent, we have minus x. We evaluate this first at 2, and then we subtract it, evaluate it at minus 1. So we substitute 2 in here, minus, and this is the whole of this bottom one substituted into that antiderivative. A lot of calculation. I expect you to be able to do this calculation to get the problems right. And here it is negative 2 1/4. And I guess I guessed right because I was saying these numbers or these areas look bigger than that one. Let's do another problem. This is a word problem. This is how you would find the total profit from the marginal profit. Now, what happens here is sometimes you're losing money, sometimes you're making money. So what's the total profit overall? What's the net profit? So here you have an airlines, and this is their marginal profit. Now the word marginal, we've talked about this before. Marginal means derivative. So this is the derivative of the profit function, and that is the square root of x minus 6. So find the total profit when 60 seats are sold. Okay, so we need to integrate to find the profit with 60. So the profit of 60 is equal to the area, and it's the net because here they were losing money, from 0 to 60 of p prime dx. So this is the square root of x minus 6 with respect to x, and now this is x to the 1/2. So we add 1 to the exponent, getting 3/2, dividing by the new exponent, which is 3/2. But when you divide by 3/2, you're multiplying by 2/3, minus, we know that the antiderivative of 6 is 6x. We're evaluating that at 60 and subtracting it evaluated at 0. Now this is very easy to evaluate at 0. It's just 0 because there's an x in each of those. So we're going to put 60 into that expression, and we get this using a calculator. So when 60 seats are sold, they're still losing money. And the reason it's thousands is because they told us, they told us the units were in hundreds of dollars per seat. So it loses this much on that flight. They really needed to get more seats filled in order to make a profit. Now, tying this back to something we've talked about before, if the location of an object relative to a starting point is s of t at time t, then the derivative with respect to time this time is s prime of t is the velocity at time t, and that's the velocity at time t as it says. And if we take the second derivative of s with respect to t again, that's the derivative of the velocity, and that's the acceleration a of t at time t. So if we are given information about the acceleration of an object, we may be able to use integration to determine information about its velocity and its location. These were the initial value problems that we talked about when we were doing antiderivatives in section 4.1. So let's do an example here where that is being applied. So this is dealing with braking distances. So you have someone named Juanita driving her car, and this is how fast she is driving her car. And they give it in miles per hour and also feet per second when she applies the brakes. And the car comes to a stop after 7 seconds. So that was her braking time. Her acceleration during the time she slows to a stop is given by a of t. This is the second derivative, is equal to minus 2.394 times t, where t is between 0 and 7. Find Juanita's velocity function, v of t, over 0 to 7. Well, to find the velocity, we integrate the acceleration. So v of t is equal to the indefinite integral of this, minus 2.394 t with respect to t. Now this number just sits there, but this is t to the 1. So I add 1 to the exponent and divide by the new exponent plus c. And so this is her velocity function. Now, when Juanita applied the brakes at time t equals 0, her velocity was this in feet per second. So we're going to substitute this into this equation and solve for c. So we use the initial equation, we put this in, her velocity, we put that in for v of t, 58.67, and we substitute 0 in, and we find c is actually equal to 58.67. Thus, her velocity function is this, and we now have figured out what c had to be because of the initial condition. Now, perhaps even the more interesting question is, how far did the car travel while she was braking? Well, the distance the car traveled is given by the definite integral of v of t over the interval from 0 to 7. Now we found that v of t was this function, so we're putting that in here and we're integrating that from 0 to 7 with respect to t. Now this number just sits there, but this is t squared. We add 1 to the exponent and divide by the new exponent. Plus, here we have just a constant times t to the 0, if you will. So we add 1 to the exponent, divide by the new exponent, and we get this. And we're evaluating these at 7, and we're subtracting these evaluated at 0. Now, at 0, that's really easy to calculate because it's going to be 0, but plugging 7 in, we need to do this. We do the calculation, and we get this number. So you see it took her 273.83, almost 274 feet to stop. And what we ended up doing is we found this area. Kind of cool, isn't it? In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.